I'd like to share some work from the TM-Form Innovation Hub that was showcased at the recent DTW conference in Copenhagen. This work is on something called carbon-aware software. And this is the concept that software itself can be aware about how carbon-intensive the electricity grid is and adjust its own behaviour to maximise the use of renewable energy. And this is part of the TM-Form ODA canvas. We have a carbon management operator which can automate normal software becoming carbon aware and therefore helping reduce the impact or the carbon impact of that software when it's running. I'm going to take you through how this operator works and the impact it can have. So firstly, this is the problem. Emissions from ICT constitute between 2 and 4% of global emissions, and this figure is growing, so it's a critical area that we need to address. The data centers that are causing this, they're always on, but actually the grids fluctuate between clean and dirty energy. And so the same computation at different times or in different places in the world, if you can swap workloads to different regions, the same computation can actually cause different amounts of carbon to be released into the atmosphere. And this is where the carbon-aware software comes in. So carbon-aware software is software that measures the carbon footprint of computing operations and dynamically alters its own behavior to reduce emissions. So it's optimizing when, where, and how applications execute. And from an IEEE publication, it shows that you can actually reduce, through adopting these techniques, you can reduce the carbon emissions from between 45 and 99%. And there are 3 pillars of how you can do this. So the first one is time shifting. So if it's possible to schedule workloads, then scheduling it for when the grid has abundant renewable energy will dramatically reduce the carbon intensity. Clearly that requires workloads that can be shifted. So things like machine learning training or doing software updates or like batch or non-real-time event processing. So you need to have workloads that can be shifted. The second one is actually location shifting. So it's deploying workloads to data centers in regions with clean energy grids. And here's an example. So at one moment in time, you might find that the Nordic region has a much greener grid than, for example, Frankfurt. And therefore, if you've got workloads that can be shifted in location, i.e. they're not latency sensitive to customers, in this case in Germany, then you shift those workloads to reduce the carbon intensity. And the third one is, and this is the one we're going to focus on today, is shaping your demand. So it's actually dynamically scaling your own capacity based on real-time carbon intensity. So in periods where the electricity grid where you're operating has high carbon, then you reduce your task, you go into effectively an eco mode. And at times when the grid where you're operating is green, is low carbon, then you scale up and you process any backlog that you may have. And the idea of this carbon operator, it provides the services to do this automatically without people having to rewrite existing software. And this is just to put in a bit of context of where this sits. So this work is part of this TM-Form ODA canvas. And this software operator is actually a Kubernetes operator for dynamically scaling control. And the way in which it works is when you have an ODA component, you can declare, or the developer of that component can declare certain microservices to be carbon aware. And the concept is microservices can be dynamically adjusted, their operations can be adjusted. You declare them as being carbon aware. You don't actually have to make any code changes in those microservices. And the way in which this works is a component declares its requirements for carbon aware processing. And then in the canvas, you have this carbon management operator. And what this does is it periodically queries real-time carbon intensity data from the zone where it's operating. And it uses that then to dynamically schedule the workloads of that component. And it's actually built on something called KEDA, on a KEDA scaled object. And so the concept is this carbon management operator, it does the hard work of actually querying and getting the carbon intensity data and then using that to dynamically scale your component based on the requirements that you've set as the developer of that component. And this graph, it just shows an example of the carbon intensity of a grid, and it's showing some sample data from the EU Frankfurt region. And what this does, it shows that over a period of 24 hours, the carbon intensity does vary. So, for example, in the middle of the night, typically when there's renewable energy on the grid, but not many consumers, then you'll find the carbon intensity goes right down. And also in the middle of the day, when there's lots of solar energy on the grid, the carbon intensity goes down. But like you see here, like the worst time is normally evening times, where you have people at home doing their cooking and other activities. And this causes actually the carbon intensity to go up. And the way in which this work operates is there's a TM-Form performance API that provides this carbon intensity data towards the operator. So in the ODA canvas, there's an API exposed that offers this TM-Form 628, which is a general purpose performance API. And we've created within that a performance showing the carbon performance for the electricity. What it actually does is it retrieves the current, and for half-hour intervals, it shows the projected carbon intensity for the electricity where that API is hosted. And the way in which the development team declare their requirements, so we've created a custom resource, a carbon management custom resource, where basically you can set some rules using a declarative method. And so there's a YAML file you include as part of your component, and you set some rules, and you're setting rules basically saying, based on the business activities that your software does, in different levels of carbon intensity, you can then declare how that should impact the scaling of your software. And this declarative configuration actually then creates a trigger into this KEDA, which is a standard Kubernetes resource. And the KEDA trigger is actually the thing that scales your deployments. And this is just showing then what it looks like. So when you do that, you provide a declarative requirement. And then what you do, your deployments where you want this to be applied. So you don't have to apply it to every single microservice in your component. So typically, real-time microservices may be offering a real-time API. You wouldn't use this because they need to be there the whole time. But some back-end processing microservices, you would then label them to say, for this deployment, carbon aware is enabled. So you're declaring that you want to apply whatever policy you've described to certain microservices within your component. And this example is a product order processor. So something which is doing not real time, but near real time order processing, where there can be some acceptance of delaying some of this processing. You can label it to say this is carbon aware. And then this is what happens. So in a period where the grid is very red, so there's high carbon intensity, then this operator will constrain the number of replicas of those microservices that have been declared to be carbon aware. And so you can see in this example, when the carbon intensity was more than 550 grams per kilowatt hour, then it's constraining a particular microservice to only have a maximum of one pod. And then what will happen is, if this is a back-end processing, you might find the order queue building up, but that's deemed to be acceptable. And so as part of this implementation, in that component, we are offering business metrics. And for example, one business metric is how long is the pending order queue? And so you can see this, the component is offering this business metric, and then that's what's then driving this auto scaling, including considering the carbon intensity. And it's considered that acceptable to allow the order queue to grow. In this case, it's showing the order queue of 35. And then what happens is, as the grid becomes greener, and now the carbon intensity has gone down, the operator then allows this deployment to scale up in order to process that backlog. And so you can see in this case, that pod is scaled up to 9 instances, and it incrementally scaled it. And it's basically saying, because the grid is much greener, you can now, it's still using this business metric of the order queue backlog, and it'll scale up temporarily while it processes that backlog. And if there's no backlog to process, it wouldn't scale up. So it's using a business metric as well as this carbon intensity data. And this shows a graph of this in action. So for this, we simulated 80 orders being placed And we did it twice, once during a high carbon electricity grid, and once during a low carbon electricity grid. And then these 3 graphs show different views of that. But in both cases, it was the same number of orders. And in this first one, it's showing how many back-end microservices, how many running pods do we allow to scale for the order processor. And you say, in this case, we restricted it to 1 to allow a backlog to build and to not use electricity during this high carbon period. And when the energy grid was low carbon, actually you let it scale right up. And this also then shows the energy consumption. And you can see when we let it scale up, it's consuming far more energy. But of course, this isn't a problem because this is consuming energy when the grid is green. So you're actually consuming a lot of renewable energy. And then this also shows the order completion rate. And you see when we were constraining it, clearly you're then having much fewer orders being completed. But in the second scenario, with the low carbon grid, you're going to burst through those orders. So this is the key part of this, is what happens is orders queue up during high carbon periods and the backlog is then processed in burst when the grid becomes green, and energy will increase during that processing, but it's using green energy. And the benefit is we have this demand side control to maximize the use of low carbon electricity. So this is the summary. So this is the first operator, the first carbon aware operator that we've managed to develop. And our takeaways are carbon aware demand shaping actually works. We're able to do this with no code changes to the microservice of our components. We took an existing component. We didn't have to make any code changes. It's all done by adding these additional YAML declarative declarations to set the policy and to determine which microservices you wanted to be carbon aware. We are going to extend this further. So as I mentioned earlier, there's multiple ways in which you can make software carbon aware. So we can look at how we do location shifting across a multi-region deployment. So you can actually dynamically use energy in a greener or low carbon region and do that dynamically based on real-time data. We're going to integrate this into the Model as a Service AI operator. So we're not just shaping the carbon intensity of the workloads we're actually using, but actually shaping our consumption of AI workloads, because clearly those have a big carbon impact. And then the third one is our plan is also to publish this carbon intensity data as part of our software marketplace. It's almost like to encourage teams building components to make them carbon aware, and you'll actually be able to see this as part of a component selection process. I'll say if you want to contribute, this is part of this TM-Form Innovation Hub. All the code is at github.com/TM-Form-ODA, and it's in the ODA Canvas repository. And then finally, I'll give a big shout out to Adarsh, who actually developed this work. Adarsh is one of our developers working on this TM-Form Innovation Hub. So well done to Adarsh. And if other people want to join, do a Google search for the TM-Form Innovation Hub and all the details will appear there. Okay, thank you very much.